And let me, first of all, congratulate the organizers for choosing our speaker today. Those of you that haven't seen him, in 1 hour from now, you will realize that this will be a real visionary talk. So let me introduce a little bit Kevin Carlberg. Kevin did his PhD and worked for a while in Stanford with Professor Farhad. Then he moved to Sandia National Lab, where he organized his own team and keep on with his excellent and good work. And now he's in Facebook and jointly in the University of Washington, keeping up with the great results. So I don't want to spoil anything. Kevin, the floor is yours, and please enjoy and let us enjoy your talk.
Great, thank you so much. Great. Well, thank you so much for the kind introduction, Antonio. It's my pleasure to be here. I want to thank all the organizers for inviting me to give the visionary talk today. So the topic of my talk today will be nonlinear model reduction, which essentially amounts to using AI methods to enable rapid simulation of extreme scale physics models. And as I'll kind of discuss over the next 60 minutes, compared to model reduction as of maybe 20 years ago, a lot of the innovations that have been occurring over the last 10 years focus a lot on leveraging deep learning techniques to move beyond some of the linear approximations that have classically underpinned the field. And before I get too far into details, I want to give a quick disclaimer at the top, which is even though I do work at Meta, formerly Facebook, none of the work I'm actually presenting today is Meta related directly. And I'm not representing the opinions of Meta in any way over the remainder of the talk. This is, I'm representing the University of Washington today. And I also want to point out that a lot of the results I'll be showing today were done primarily by my former postdocs, Kuk-Jin Lee and Eric Parrish at Sandia National Labs. And Eric was the von Neumann Fellow there. Okay, so what's the motivation for this work? So I'm sure everyone in the audience here is very aware of the importance of high fidelity modeling and simulation. And as we all know, high fidelity physics-based modeling has become indispensable across a wide range of applications in science and engineering and even entertainment, as it provides a mechanism to accurately simulate realistic performance of complex engineered physical systems, the performance of autonomous agents embodied in an environment, and the physical movement of virtual characters in films, and even interactions with virtual objects as we do in virtual reality. As such, physics-based simulations not only play a critical role in the national security work done at my previous employer, Sandia National Labs, it also plays a surprisingly large role in the virtual and augmented reality research and ultimately the metaverse work going on at Meta. However, as we rely more and more on these simulations for decision-making, design, and immersive experiences, we place greater demands on simulation fidelity. To ensure that these models have high predictive fidelity, we obviously must imbue them with fine spatiotemporal resolution, which leads to computational models that correspond to extreme scale nonlinear dynamical systems. And so whether we're talking about turbulent reacting flows, Antarctic ice sheet modeling, or MHD simulations going on at Sandia, we get the same kind of trend where we get these extremely sort of high resolution, but also expensive simulations. And that introduces a de facto computational barrier that prevents us from using these high fidelity predictive models for a range of time critical problems that we really care about and that are important. For example, model predictive control requires executing simulations in real time. Health monitoring of, let's say, critical infrastructure requires us to execute simulations on the order of minutes or hours. Interactive virtual environments require the support of physics engines that can render real-time interactive rates. And design optimization requires simulations to execute on the order of, let's say, a few days. And so the overall goal of this work really is to break this computational barrier so we can employ these high fidelity predictive models for these time critical applications. So here's one application that people in the audience may not be as familiar with, which is virtual reality. So this is actually an example from Meta, where we have somebody interacting in VR in an OptiTrack system where they have fine digit tracking, and they're playing a game of Jenga. And Jenga is actually a good fit for current physics engines like PhysX that rely on rigid body dynamics because the blocks themselves are rigid bodies. However, you might notice that some of the contact that's required to actually pick up these objects looks a little bit jittery and unreliable. For example, picking up the duck requires carefully grabbing this object with two hands and placing it atop this tower. And the reason for this is that these physics engines rely on rigid body dynamics. So it's impossible essentially to render realistic contact forces because, as we know, when rigid bodies interact, the contact occurs on a set of measures 0. So a lot of engineering hacks have to be implemented in order to get contact and grip and touch to even occur in VR. So obviously we like to push this boundary so we can use much higher fidelity simulations for these interactive experiences we hope to experience in the metaverse. Going back to a more kind of familiar example in science and engineering, this is an example from my previous employer. We were focused on the so-called captive carry problem, where the objective is to compute the pressure exerted on the store when it's placed in a three-dimensional cavity over very long time intervals. So to model this, our analysts at Sandia, in particular Matthew Baroni and Srini Arudagenesan, developed a validated hybrid RANS LES model that is accurate to within 5% of experiments in our quantity of interest over a wide range of Mach numbers. And as you can see on the left, the pressure exerted on the store looks reasonable, and actually it is validated according to our physical experiments. On the right, I'm showing a two-dimensional slice through that three-dimensional cavity and visualizing the gradient of the density field. So all these results are great in terms of accuracy. To obtain these predictive results, we needed to imbue very fine spatiotemporal resolution. So just the CFD model on the right is characterized by 100 million cells and 200,000 time steps. And this is actually very common in CFD, as many of us know, as RANS models are not able to accurately predict regions of separated turbulent flow. And so just to give you a picture of sort of like how expensive the simulation is, even at Sandia, where we have access to some of the world's largest supercomputers, just six of these simulations running concurrently completely maxes out our allocation on the supercomputer. And that's because a single simulation consumes 6 weeks on 5,000 cores. So clearly, while this might be a reasonable cost to incur for executing a few simulations at a few points in design space, it's really not practical it's not practical to deploy this model on a range of time critical applications that we care about. For example, a thorough exploration of the flight envelope is really out of the question with this costly model. Uncertainty quantification is also not really practical. Model predictive control, as well as robust design of the store and cavity, which might entail some sort of stochastic design optimization. All of these are unachievable due to this computational cost incurred by these high fidelity predictive models. Some of you may have seen the high performance fast computing challenge issued by NASA a few years ago, and that actually articulated this barrier quite well. So a few snippets from their challenge. Despite tremendous progress made in the past few decades, CFD tools are too slow for simulation of complex geometry flows, taking from thousands to millions of computational core hours. So they're basically articulating this barrier directly. Their time-critical problem is actually multidisciplinary analysis and design, where they want to speed up they want to accelerate computations by orders of magnitude, and actually they call out specific numbers of 10x all the way to 1000x. And I'll show later on in this talk how we've made progress towards getting these performance speedups simply by applying AI methods to reduce the dimensionality and complexity of these simulations. Okay, so this is the motivation, as hopefully have convinced you, across entertainment, classical science and engineering, as well as in sort of the aerospace industry. We have a strong need to accelerate these simulations. So how do we even begin to tackle this problem in sort of a general way that's not overly focused and bespoke to a specific application? We're going to assume that our high-fidelity. Sorry, I'm hearing maybe Solid could. Okay, so the overall mathematical formulation that we adopted for the high fidelity model is sorry, I think Solid is I'm getting a lot of feedback. So. Okay, so the overall approach that we're adopting is one of assuming that the high fidelity model corresponds to a system of parameterized nonlinear ODEs. So I'm expressing that sort of formulation right here. X is our state vector, which let's say it's of dimension 100 million, for example. F is our velocity vector, which is nonlinear in the state. And mu denote parameters that define different instances of this problem. So these are generally design variables, boundary conditions, initial conditions, and so on. We have initial condition that may depend on the parameters, a finite time interval, and our parameters live in some parameter domain, calligraphic D. So how do we characterize a time-critical problem? In the most general setting, a time-critical problem merely states that we have to rapidly solve this ODE for many points in the parameter space. And rapidity is sort of defined by the application at hand. So if we're doing, like, let's say a VR simulation, then we must achieve real-time interactive rates. If we're talking about a design optimization process, we may be able to incur on the order of a week for a single simulation. And so this is the overall sort of formulation that we'll begin with. And later on, we'll particularize this formulation to specific problems of interest. So how are we going to begin to pursue this problem? We're going to start with by basically making an observation that we can exploit simulation data that we collect at a small subset of points. So let's say we have to query on the order of 1,000 points. The hypothesis is that we can actually run a subset of simulations in high fidelity, glean all the data generated from those simulations for important structure, and then leverage that structure to make the simulation run much faster at the remaining points that we care about, while inheriting important properties like accuracy, sort of error quantification, as well as preserving important physical properties. So all the methods that I'm going to present today follow the same sort of 3-step meta algorithm. The first step in this algorithm is training. We're going to execute this expensive simulation at a handful of points that I'm going to denote in red here, and collect simulation data. And I'll prescribe later on the exact nature of the simulation data, but it will range from solution snapshots all the way to collecting examples of the reduced order model error. Number 2, we apply machine learning to that data to identify important structure that we can leverage for step 3, which is reduction. So step 3 basically takes all the structure we've learned in step 2 and leverages it to make the model run much faster at the remaining points shown in blue. So this is a sort of general 3-step meta algorithm. And to ground this, I'm going to present this 3-step meta algorithm in terms of classical POD, which many people in the audience are familiar with. So in POD, what do? We take a 1 point in parameter space, we execute a transient dynamic simulation. At every time step, we save the state vector X as a column in this matrix that we're going to generate by concatenating these vectors together. So at the end of a single simulation, we have an n by t matrix where t is the number of time steps and n is the number of degrees of freedom in our model. So ballpark, let's say n is about 100 million and t is about 100,000. So we repeat this at several other points in parameter space, concatenate all these vectors together, and this yields the snapshot matrix, where each column is the spatially distributed solution at a single instance in time and parameters. So that's step 1. We collect all our simulation data in the form of solution snapshots. Step 2 is to perform machine learning on this data. And so what POD does is it actually computes the principal components of that data. So it's up to you to decide if that's actually machine learning. It's been around since 1904. So it's maybe one of the original machine learning methods, but essentially we compute the thin singular value decomposition of this matrix. We truncate the left singular vectors to preserve only the dominant modes, which we often call the POD modes. And we basically view that as a subspace that we're going to use to approximate our solution in step 3. And so the way we interpret phi, they basically are the principal components corresponding to the spatial simulation data that we've generated. So now that we've gleaned our data for this sort of low dimensional structure, step 3 aims to reduce the cost of solving this ODE at the points in parameter space that we care about. So we do this in 2 steps. The first is kinematic approximation, and the second is dynamic approximation. So for kinematics, we approximate our state X as X tilde, which we enforce to reside in the space spanned by the columns of phi. So this simple algebraic expression essentially reduces the number of degrees of freedom from, say, 100 million down to on the order of 100. So this green vector X hat is on the order of 100. So we've enforced the state to live in this low dimensional subspace of the high dimensional of Rn. How do we then project the governing equations onto the subspace? And there are really 2 dominant approaches. We first start with our high fidelity model expressed as an ODE. I'm suppressing dependence on parameters for simplicity here. So imagine this is the high fidelity model instantiated at a specific point in parameter space. We can also write this ODE in residual form, right, where the residual is just the misfit of the left and right hand sides here. So many of us are familiar with the Galerkin, so-called Galerkin projection method, which is actually equivalent to performing residual minimizing projection at the time continuous level. So we're all familiar with the top equation here, which is just simply a Galerkin projection that reduces the number of degrees of freedom down substantially. But it turns out this is actually equivalent mathematically to minimizing the L2 norm of that time continuous residual, assuming that phi is an orthogonal matrix, which we assume it to be. And so we can interpret Galerkin projection as essentially a time continuous residual minimizing approximation. However, as we all know, in order to actually resolve this in time, we must introduce a time discretization method. Let's imagine it's a linear multi-step scheme, although we can consider Runge-Kutta schemes or any other kind of scheme as well. And then we essentially have to discretize this ODE in time. And so what we can see here, why I'm denoting the Galerkin ROM O delta E in red, is that you can actually show that the time discrete solution generated by Galerkin projection generally does not satisfy any notion of optimality. So the optimality property we achieve at the time continuous level in general is lost at the time discrete level. And as we showed in some of our work, this can yield really substantial problems especially when we deal with stiff ODEs as we often obtain in turbulence. So the approach that we instead propose is to flip the order of time discretization and optimization. And this yields what we call the least squares Petrov-Galerkin ROM O delta E, or LSPG ROM, where we introduce a residual minimizing projection at the time discrete level directly. And as I'll show a little bit later, flipping the order of time discretization and projection allows for much more stable and accurate long-time predictions, especially when we have stiff ODEs. I'll just point out there's a whole family of other residual minimizing ROMs that have been developed in the literature. And in particular, my postdoc, Eric, and I published a paper 2 years ago where we actually generalized this notion of LSPG model reduction in a manner that allows us to decouple the projection, the time window for projection from the time step taken for discretization. Because in general, there's no reason that our time step that we take within our time integrator has to match the time window that we employ for projecting the dynamics. And so if you're interested, that paper kind of goes into detail in terms of how we do windowed space-time LSPG projection. Either way, let's see how these methods work on a practical problem in engineering. So here's the captive carry problem. Unsteady Navier-Stokes, Reynolds number of 6 million, Mach number of 0.6. We have 1,000,000 degrees of freedom in our spatial discretization and 10,000 time steps. So one implementation detail I didn't have time to really go into detail on is how we actually solve the system of equations at each time instance. So in its plain form here, by minimizing the residual in the L2 norm over all elements of the trial subspace, this is going to actually be quite expensive, and it'll scale linearly with the original discretization of the problem. And that's because we're minimizing the sum of squares of 1,000,000 residual elements in this plain form for LSPG. So to get around this, we adopt the hyper reduction approach, which has been, it's quite widespread now in the literature. But what we essentially do in this setting is we introduce a semi-norm denoted by theta here that requires us to evaluate the residual on only a small subset of the mesh. And we generate theta through a gappy POD procedure. And so the subset of the mesh that we must evaluate the residual on is shown in red here. And this is less than 1% of the mesh, actually, and it allows us to actually execute HPC caliber simulations on a laptop. And so the results that we obtain are shown below. These are some of the first results for orders of magnitude acceleration of model reduction applied to turbulent flows. The top row is the LSPG ROM executing in half an hour on my laptop. The bottom was the high fidelity model, 5 hours on 48 cores. So we get 2 orders of magnitude cost reduction with sub 1% errors in the time average drag, which actually does hit the criteria that NASA laid out in their call earlier. I want to point out here that the parameterization that we're introducing, that mu parameter, is time, in that what we are doing is we're training the ROM over a time window and then doing prediction out beyond the final time for prediction. So these seem like promising results, and we've obtained similar results across the domain of fluid dynamics. So a natural question is, why doesn't everybody use ROMs, right? If these results are so great, why isn't this come packaged with every computational mechanics code that we use on a regular basis? And that's because really, if we introduce drastic parameter variation in this problem, we're going to get quite poor results using vanilla model reduction methods. And that's for a number of reasons. And I'm going to go over today 3 of these core reasons why model reduction is not more widespread, which I'm calling outstanding challenges in model reduction, and steps that we've taken to overcome these shortcomings in the state of the art. So the first is that the linear subspace assumption is very strong. So even on slide 4, I introduced this approximation that underpins nearly every model reduction method, which is that our state lives in a low dimensional subspace of the high dimensional solution space. So no matter how I compute phi, essentially what I'm saying is that the state lives in a low dimensional linear subspace of the original state space. This in and of itself is extremely strong. And even in simple cases where, let's imagine we have a one-dimensional advection dominated problem like Berger's equation, you can prove that there exists no low-dimensional linear subspace that can accurately capture all solutions in that trajectory. And mathematically, this is known as a slowly decaying Kolmogorov width. So to overcome this, we did some work that we published last year that shows us how to, sort of is the first step in overcoming this linear subspace assumption shortcoming in a general way that leverages nonlinear manifolds. The second is that important physical properties generally are not enforced. So these Galerkin and LSPG projection methods and most other projection methods that have been used are sort of physics agnostic, in that we are doing least squares projections, which is going to minimize the sum of squares of misfits of the reduced order model sort of residual physics to the high fidelity physics, but there's no guarantee that we're going to conserve we're going to imbue our reduced order model with properties like preserving symplectic time evolution, inheriting conservation laws, and so on. And so I'm going to present a little bit of work on how we've extended these models to guarantee exact satisfaction of conservation laws for finite volume schemes. And number three is that error analysis is generally very difficult. So if you're familiar with the literature in model reduction, you know that there's a rich history of developing both rigorous a priori and a posteriori error bounds that bound the error in our reduced order model solution by a deterministic number that is calculated via analysis. And while that's often nice and it can give analysts some idea of the error incurred by their model, it's actually not that useful for the kinds of problems that we're tackling today. And that's because for nonlinear dynamical systems, most of these error bounds are derived by accumulating the worst case error at each time instance. So this yields exponentially growing bounds that are often extremely pessimistic and overestimate the error by orders of magnitude. Further, we often use these models within an uncertainty quantification context. And so having a measure of the uncertainty in the full order model solution based on the ROM simulation would be much more useful because we could characterize it as a source of epistemic uncertainty. And so towards that end, we pioneered a few methods in adopting an alternative approach to error analysis that leverages statistical learning to build validated statistical models of the reduced order model error. So this will be an outline for the rest of the talk today. Okay, so let's first start with the linear subspace assumption being strong. So I'm not going to assume that everyone in the audience is familiar with the Kolmogorov width limitation of linear subspaces. So we'll start with a few mathematical definitions and then get into the core argument. So first I'll introduce calligraphic M, which is the solution manifold. It's essentially the set of all solutions, X over T and mu. So this is basically all the set of solutions that we would obtain for all values of T and all values of the parameter. I'm going to also introduce calligraphic SP, which is the set of all p-dimensional linear subspaces of Rn. This is known as the Grassmann manifold. So the Kolmogorov p-width of this manifold is nothing more than the infomizer over all p-dimensional linear subspaces of p infinity ms, where p infinity ms is the L infinity projection error of that manifold onto the subspace. So what this basically means is that if the Kolmogorov p-width for a manifold is small, there exists some linear subspace that can accurately capture every element of that solution manifold. So because it's a little bit challenging to do calculations with the L infinity norm, for illustration, I'm going to replace that for now with the L2 norm, and then I'll plot the decay of the Kolmogorov width for a specific problem that I'll get into more details on later on. So this is a typical sort of decay that we observe for the Kolmogorov width for a problem. So we see as we increase P, the Kolmogorov width decays monotonically in an exponential manner. So what I can do now is plot actually the L2 projection error of the manifold onto a POD basis computed from data. And if I do that, I obtain this blue curve. We see that this blue curve is obviously lower bounded by the black curve, and the gap there can be characterized as the training deficiency, right? We can make these curves coincident if we include infinite training data in our POD basis. So now what I'll do is I'll plot the relative L2 error of the LSPG reduced order model constructed with that POD basis on the same exact plot. So what we get are these green points here. And the gap between these green points in the blue curve is known as the closure error. It's essentially the failure of the reduced order model to reproduce the projection of the solution onto the underlying solution space subspace itself. So while our community has done a lot of work in terms of characterizing both the training deficiency and the closure error, we haven't really asked in many cases, how good is this black curve? Is this actually something that's acceptable? And what I'm going to argue is this, in this example, it's actually a quite poor result, because the underlying solution manifold in this case is of dimension 3. And that's because in this case, we have actually two parameters that I'll explain later on, as well as time. And so there's a unique mapping, because it's a well-posed initial value problem. There's a unique mapping from three numbers, time, mu1, and mu2, to the solution itself. So that defines a parameterization function of a three-dimensional manifold that's embedded within Rn. And so the fact that we are restricting our attention to linear subspaces already incurs a substantial penalty, even when the underlying solution subspace, even when the underlying low-dimensional subspace is the exact same dimension as the true intrinsic dimension of the manifold itself. So in this case, we incur a 5% penalty just by introducing a linear subspace to begin with. And this is called the Kolmogorov width limitation of linear subspaces, because when we set the dimension of the subspace equal to the dimension of the true manifold, we incur substantial error. So the goal is to overcome this fundamental shortcoming of linear subspaces by projecting onto a nonlinear manifold in a way that is that doesn't require too much knowledge of the problem at hand and can be automated and scaled up in a tractable way. So we're not the first people to recognize this issue. It's actually been a very hot topic in model reduction over the past few decades. But most methods, I would say, that have been developed don't quite hit the mark in terms of developing general nonlinear manifold methods that allow us to sort of apply a turn crank method as we do with POD to overcome this limitation. So the most popular category of methods still leverage a linear subspace, but they basically transform or update the linear subspace in some way to improve approximation properties. So whether we're talking about methods of freezing, coordinate transformation, shifted POD, snapshot transformation, Lagrangian formulation, and lax pairs, all these methods essentially sort of advect the basis in some way to better capture the solution characteristics. The main downside is that these methods often require very extreme problem-specific knowledge to work well, and they don't really consider manifolds of general nonlinear structure. Another approach is to construct a priori local linear subspaces of specific regions of the space domain, time domain, or state space itself. And you can see some references here. And again, the main downside of these methods, in my view, is that they require a lot of pre-processing sort of understanding of the state space, spatial domain, and time domain, and they don't really consider manifolds of general nonlinear structure either. So when we started this work, there were basically 3 papers that we found that did model reduction on nonlinear manifolds, but these suffered from kinematic inconsistency in that the velocity did not reside in the tangent space of the manifold. They were, in one case, limited to piecewise linear manifolds, and the solutions generally lacked optimality. So the goals of this work were mainly twofold. One, we wanted to overcome shortcomings of these existing methods by supporting general nonlinear manifolds. We wanted to obviously enforce kinematic consistency, and we wanted our ROM solution to satisfy optimality properties similar to what we had achieved with Galerkin and LSPG projection in the linear subspace case. And secondarily, we want the manifold construction to be practical, in that we don't want to require any problem-specific knowledge. We want to be able to use the same training data as POD, such that we can essentially scale this up in a seamless manner. So for the first of these, I'm going to propose a manifold Galerkin and LSPG set of projection techniques that don't rely on deep learning at all. This is just differential geometry in dynamical systems. And the second is going to leverage deep learning, in particular deep convolutional autoencoders as a mechanism for generating practical nonlinear manifolds. But I want to point out that even though we employed deep convolutional autoencoders in our work, we could still leverage manifold Galerkin and LSPG projection with other approaches to generating manifolds. So I'll first start with the first component here, manifold Galerkin and LSPG projection. So how do we, in our paper, we go into extreme detail in terms of how we develop this. I'm going to provide a high-level view on the way in which we go about developing these nonlinear projection methods onto nonlinear manifolds. So in the case of linear trial subspaces like POD, our subspace was defined as the range of phi, right? The set of all solutions phi x hat, where x is in Rp. So for n equals 3 and p equals 2, this is just a plane in R3. And by enforcing the solution to reside in the subspace, we can write these simple algebraic expressions down, right? This should be very familiar and not surprising. So if we move to a nonlinear trial manifold, we can use a similar viewpoint. Basically, we can write calligraphic S is the set of all solutions G of x hat. And so if G is a linear mapping, we recover the left column here, but G in general can be a nonlinear mapping that we want to be twice continuously differentiable. So this is essentially viewing the nonlinear manifold from the extrinsic view through a parameterization function G. So for n equals 3 and p equals 2, we might obtain this sort of curved manifold, submanifold of R3. If we want the state to reside in that manifold, we can simply write x tilde equals G of x hat, which allows us to imbue the manifold with general structure. And by applying the chain rule, we then observe that the velocity must live in the tangent space of the manifold, so it's expressed as a linear combination of the Jacobian of that decoder. And this allows us to ensure kinematic consistency. So this is the kinematic approximation we leverage. How do we then introduce a dynamics approximation? So in the linear subspace case, you recall we were given phi. We then derived the Galerkin projection by doing least squares minimization of the velocity onto the kinematic approximation space of the velocity, which yielded this system of ODEs. And in the LSPG case, we applied a similar approach, but at the time discrete level. So in the nonlinear manifold case, we can again introduce residual minimizing projections at the time continuous and time discrete levels. In the Galerkin case, we must introduce the kinematic approximation for the velocity which, as I mentioned, is the decoder Jacobian post-multiplied by the generalized coordinates that we want to compute, which then yields this system of ODEs that we need to integrate in time. I want to point out that because the ODE is expressed in terms of the generalized coordinates, we can use any time integrator to evolve the solution. We're guaranteed to still live in the manifold itself through application of the decoder function. So this gets around a lot of the issues that people often encounter with integrating solutions on manifolds. We essentially, do all the integration in terms of the latent variables that are within the parameterization function, and then any application of the parameterization function guarantees the resulting solution will live on that manifold. In the LSPG case, we have a similar expression to the one on the left. And so we can see here that by adopting this approach, we satisfy residual minimization at the time continuous and time discrete levels, respectively. So in our paper, we actually prove equivalence of these two approaches in certain conditions. So if we have a sufficiently smooth manifold and the limit of the time step going to 0, as well as solution increments bounded by the time step size itself, then we can prove that these two projection schemes become equivalent. And this is sensible because time discrete projection becomes equivalent to time continuous projection in the limit of the time step going to 0 under these conditions. We also derived error bounds for these methods, rigorous a posteriori error bounds. Again, under modest conditions, we can bound the Galerkin and the LSPG errors from above by very similar quantities. The gray terms on the right are just the recursive term in the bound, which are shared across both approximations. They differ in terms of the colored terms there. And what we see is because we are doing time discrete error analysis and we are minimizing the L2 norm of the time discrete residual with LSPG, the manifold LSPG method actually sequentially minimizes the error bound, which is a nice result to have. So that gives us some early assurance that our LSPG model will generate good results. So now that we've introduced at a high level these manifold LSPG and Galerkin methods, how can we construct this manifold in a practical way from training data? And that gets to this next part of the talk, which we're going to leverage a deep convolutional autoencoders for. All right, and that will generate this parameterization function G that defines our manifold S from the extrinsic view. So I'm sure many in the audience are familiar with autoencoders, but essentially autoencoders are specific kinds of neural network architectures that copy inputs to outputs. So in the simplest case of all the activations of being linear, right, this would recover essentially phi transpose phi in the POD sense. But in general, we can have now nonlinear mappings that both encode and decode an input. So in the case of in our context, what we're going to do is introduce an autoencoder and try to apply that to snapshots of the state vector itself. And what you can imagine is if we're able to train this autoencoder architecture such that it successfully copies inputs to outputs, then what we've actually learned indirectly is this parameterization function G that associates with the decoder of this network. And that's because we've basically shown that through this construction, we've generated a mapping that goes from a low-dimensional space to the original state space, such that the codomain of that function covers the entire manifold itself, right? If we're able to train this with very low error. And so the idea here is we're going to apply a similar procedure to POD, but use an autoencoder instead, and then extract the decoder from that autoencoder and leverage that to define our manifold. So returning to this graphic from POD, rather than computing the SVD, we introduce an autoencoder architecture. We train the network to try to copy inputs to outputs. Each column should match. And so we basically are going to train this network by minimizing the Frobenius norm of the error between these two input and output matrices. We then define our nonlinear trial manifold by setting our decoder function, setting our parameterization function equal to the decoder. And I want to point out here that we use the exact same snapshot data as POD. We don't need any specialized problem knowledge, for example, the advection speed of waves. We only inject our knowledge of the problem and the inductive bias used to train this network. And I'll talk a little bit later on in terms of how we might choose the architecture for this autoencoder. So returning to our manifold Galerkin and LSPG formulations, now that we know that G is coming from the decoder of an autoencoder, we immediately see that basically what our ROM is doing is it's injecting deep learning predictions with physics simulations, right? So the residuals here are computed by our high-fidelity computational physics code, and the G function is generated by this decoder of the autoencoder. So our dynamical system model is directly integrating deep learning predictions with computational physics codes. So let's get into a few examples here. These are some fairly simple examples, but these are actually problems exhibiting a slowly decaying Kolmogorov width. So even though they may appear quite simple, these are actually very, very challenging problems for typical model reduction methods. So I'll first consider a simple 1D Burger's equation, where we have two parameters, the alpha term, which is in the source on the right-hand side, as well as the inlet boundary condition. We use a finite volume discretization and a backward Euler discretization. And then the 2D reacting flow case, we will consider two terms in the reaction to be our parameters, a finite difference scheme in the BDF2 integrator. And in this case, the autoencoder that we will imply is a convolutional autoencoder. And the reason that we're applying convolutional autoencoders is that we want our kinematic approximation to be able to capture features that are translationally invariant, right? So as many of us know, if you've worked at all with image data, the idea of convolutional autoencoders is that they basically inject a form of inductive bias that allows for parameter sharing, as well as nice properties that we know are intrinsic to images. For example, if we want to classify an image of a dog, we don't care if the dog is sort of small, large, or resides in a different part of the image. Convolutional architectures allow us to have this these properties of both scale and translational equivariance. And for that reason, we're going to apply that same idea to these problems, because when we have, for example, a moving shock, we want our manifold to be able to capture shocks regardless of position. So that's sort of the motivation at a high level for why we choose convolutional architectures. And again, we're going to extract the decoder to define our parameterization function. So here is the Burger's equation example. The leftmost column is the full order model solution. The middle column here, I'm going to just show the classical POD method with the dimension 3. If you recall, 3 is the actual solution, is the actual dimension of the underlying solution manifold. And what we see here is quite poor performance of POD, as we would expect, right? In the topmost plot here, I'm just plotting out the 3 generalized coordinates as they evolve in time. So if you're familiar with model reduction, you know that this is a very common result wherein we have an advective phenomenon. And because we leverage 3 spatially fixed modes to represent that, any linear combination of 3 modes will not do a good job of representing this moving discontinuity. And so again, this is sort of an instance of a problem that has a slowly decaying Kolmogorov width, because even if I add a few modes, we still are not overcoming this intrinsic property of linear subspaces not being able to capture moving advective phenomena. So now let's instead move to an autoencoder architecture. I'm going to use the exact same training data as POD, but I'm going to, instead of restricting to a linear subspace, I'm going to now move to a nonlinear autoencoder of the same dimension. And what we see here is a near perfect reconstruction. So even though I'm using the same data and the same dimension of the underlying manifold, we're able to get near perfect reconstruction of the solution. And that's again because we are breaking this Kolmogorov with barrier of linear subspaces in this approach. So this is already a very exciting result, and it basically forms the foundation for how we can introduce a dynamics model that allows us to obtain very high accuracy even in the presence of these moving discontinuities. Maybe one quick second here. Apologies for that. Sorry, there was a lot of noise outside I had to deal with. So here's actually the reduced order model that we're solving. The first 2 rows here correspond to the full order model and the POD LSPG ROM of dimension 5. And as we kind of saw in the previous slide, we get very poor reconstruction performance of the reduced order model if we use a linear subspace, in this case POD. But now if I move to a nonlinear manifold with the same LSPG projection, I get much, much better results and near perfect results, even though we're using the same dimension. So this just goes to show that the issue with model reduction in the second case was not the data. It was not even the projection. It was actually the kinematic approximation that was underpinning the reduced order model. Namely, we were using a linear subspace as opposed to a nonlinear manifold. So now let's return to these graphics that I showed earlier. So the example that I showed a few slides ago was actually the reacting flow example. And what we can see here is we have, these are the results that I showed previously for the linear subspace. So now what I'll show is the result if we do the L2 projection of the solution manifold onto the autoencoder learned manifold. And that yields these black points shown here. So you see immediately that we are able to do significantly better with this learned nonlinear manifold than even the optimal linear subspace. So right away, we have high confidence that we're overcoming this sort of fundamental limitation of linear subspaces in model reduction. If I then solve a reduced order model with this nonlinear manifold, we get the pink points shown here. Again, the gap between the pink and the black corresponds to the closure error. But we get, right away orders of magnitude more accurate results than subspace LSPG for the same dimensionality. And overall, I hope this has convinced you that this approach allows us to break the Kolmogorov-With barrier of linear subspace and model reduction. And just for completeness, I'll show the results for subspace Galerkin and manifold Galerkin. And what we see here is that manifold LSPG outperforms manifold Galerkin, and this result likely arises from that analysis result I showed earlier, where we are sequentially minimizing the error bound in the case of LSPG model reduction. So if you want more, if you're interested in diving deeper, the first reference on this slide sort of provides the full presentation of that approach. So now on to the second part of the talk, which is dealing with the challenge that important physical properties are often not enforced with model reduction. So let's consider, for the sake of argument, finite volume schemes, right? And there are obviously a wide range of different kinds of physical systems we might want to preserve the properties of in model reduction. And a lot of work has been done in that domain. We're going to consider, just for the sake of this talk, finite volume schemes. So in the case of finite volume schemes, we know that basically we are dealing with the integral form of the conservation law, right? So we decompose our spatial domain into control volumes, and we enforce exactly conservation over each of those control volumes and stitch those results together to obtain the dynamical system. So in the case of finite volume schemes, we have specific interpretations of the state variable as well as the velocity and the residual. Namely, each state variable corresponds to the average value of a conserved variable, usually mass, momentum, and energy, over a control volume. The velocity corresponds to the misfit between the flux and the source terms in our conservation law. And the residual corresponds to basically the rate of conservation violation of a given variable within a control volume. When we introduce a time discretization method, then this basically, if we use an atom scheme, for example, tells us how much we're violating conservation in each variable in each control volume over each time step. So as we all know, conservation is the intrinsic structure enforced by finite volume schemes because the high fidelity model sets these residuals to 0. So with this interpretation in mind, if we move to manifold Galerkin and manifold LSPG, what we see is that essentially these models are minimizing the sum of squares of conservation violation, either rates or over finite time steps. So while that's a nice property, right, we're minimizing the rate of or the amount of conservation violation, it doesn't actually yield any enforcement of conservation, even globally, right? So we can get spurious generation or dissipation of mass, momentum, and energy when we apply this to finite volume schemes, which can lead to really poor long-time performance. So how do we fix this? We basically leverage the optimization structure of these two projection schemes and introduce constraints that exactly enforce conservation over subdomains of the problem. And we call these conservative manifold Galerkin and conservative manifold LSPG techniques. And so by introducing just a small number of constraints, right? So C, the number of rows in C corresponds to the number of subdomains we're considering multiplied by the number of conserved variables. By introducing a small number of constraints, which we can approximate again with hyperreduction, we're able to exactly enforce conservation over subdomains of the problem. So in the simplest case of, let's say, global conservation, right, which is shown on the right here, we'll be able to introduce only on the order of, let's say, 5 constraints for three-dimensional Navier-Stokes and ensure that our reduced order model trajectory will retain global conservation. So how does this manifest itself in terms of error analysis? So it turns out you get some really nice results from the error analysis that emerges from this type of approach. In particular, the error in the conserved quantities computed with either conservative Galerkin or conservative LSPG can be bounded with this approach as shown here. And the main idea here is that the error that we get depends only on the velocity on the decomposed mesh. It doesn't depend at all on the velocity on the subset of the mesh that's contained within those subdomains. And so if we consider global conservation, for example, the error in globally conserved quantities is due entirely to the flux along the boundary, right? So errors that are incurred within that domain don't affect whatsoever the overall error in the globally conserved quantities. So that's a nice result. What we often observe in practice is when we apply this method, we get quite accurate, overall trajectories just by enforcing conservation to be prescribed on subdomains of the problem. So returning to this Burger's equation example, we have the full order model and the LSPG models. I'm considering both POD and autoencoder manifolds. And these are the results that I showed earlier. And what I want to point out here is that if we look at violation of global conservation, even though the autoencoder looks quite good, it still violates conservation on the order of 1%. So for even long time integration problems, this could sort of manifest in issues over the long haul. So what we can do is, again, equip these projection schemes with constraints related to global conservation. And if we do that, we obtain similar results in the eyeball norm. But actually, even the POD subspace with conservation constraints satisfies global conservation to within machine precision. And so, and as you see on the rightmost column, not only have we essentially cut down completely the conservation violation, our solution error is actually better as well. So just to summarize very quickly this one part of the talk, we've taken our residual minimizing projection schemes and appended equality constraints that enforce conservation over subdomains. And again, we're integrating computational physics with deep learning, both in the objective and in the constraints. I want to point out that if you look at the literature in AI, most of the latent dynamics models that they develop are purely data-driven, right? So they're not only learning the embedding, but also they're learning via LSTM models, for example, the time evolution of the dynamics. And that really prevents you from imbuing your model with some of these nice properties that we've talked about today, namely error analysis and the ability to exactly satisfy conservation laws. Very quickly, when we implement these in practice, we use AutoGrad to compute the decoder Jacobian, and AutoGrad is supported naturally by deep learning software like PyTorch, for example. And what we're working on now is hyperreduction, and that's actually not too difficult if we use a convolutional autoencoder because convolutional layers preserve sparsity. I also want to point out that we have a general optimization formulation that we've developed in collaboration with Matthew Czar and Alexander Schein that allows us to extend this notion of constrained optimization to a broader range of both kinematic and dynamic constraints that we want to imbue our reduced order model with. Okay, so the last part of the talk is on error analysis. So to motivate this, as I showed earlier, we can derive rigorous a posteriori error bounds for our reduced order models. And this is really sort of consistent with what is commonly done in the literature in model reduction. And so a natural question might be, can we just take these error bounds and implement them in our code and use these to quantify the error? So in principle, yes, we can do that. But if you draw out the recursion and write the global error bounds at a given time instance, what you'll see is that the stability constants for these error bounds grow exponentially in time. And furthermore, these error bounds are deterministic, right? Clearly, they bound the solution error by a number on the right, which doesn't lend itself naturally to uncertainty quantification, right? Because we know that the ROM is in principle introducing some source of epistemic uncertainty. So if we are doing some kind of task like forward uncertainty propagation, it'd be great if we could encode the ROM error as a source of uncertainty. And so those two observations motivate this line of work, which at the time was a new line of work in model reduction, which is what we call machine learning error models. And the key observation underpinning machine learning error models is that ROMs tend to generate quantities as an artifact of their simulation that are informative of the error. So here's a simple example from a diffusion problem where we see that some of the quantities generated by the error, which are on the x-axis here, the residual norm and the error bound, are correlated quite strongly with the actual error in the state space with respect to the high fidelity model. And so in machine learning parlance, we view these artifacts that the ROM produces as good features for predicting the error via regression. And so the core idea underpinning this line of work is to apply machine learning regression techniques to generate a mapping from residual-based quantities that the ROM generates for free to a random variable for the error whose statistics have been calibrated properly with training data. And we call this, as I mentioned, machine learning error models. So with this general formulation, we could adopt a variety of approaches. But what we would like to do is actually inform our design with sort of analysis and what we know about the problem itself. So let's begin by asking ourselves, what attributes does the ROM error have? So here's the error bound I showed earlier. A few things we notice immediately from this expression. Number one, the ROM error at a given point depends on non-local quantities in time, right? So the ROM error at time step 100 in principle is affected by the error incurred at time step 1. So we can have very long time dependence of the error bound in terms of the error that's generated across time. Number two is that the error bound depends on the residual, right? The residual dictates the misfit of the actual dynamics that we're solving, and via the problem's coercivity constants and other variables, we can bound the state space error by the residual error according to the stability constants. And so the regression model that we're going to adopt leverages these two observations to bake in inductive biases that we hypothesize will yield accurate regression models for the purpose of error prediction. So what we're going to do is decompose our error prediction into a deterministic and a stochastic component. The deterministic component, we will use a recurrent neural network architecture. What we're showing here is basically that this delta F is going to be determined at a given time step as a function of the features rho, as well as a latent state H, which we will learn, of course, as well as the error at the previous time step. And H will be evolved according to some latent state dynamics that are related to the error in the reduced order model. And so these latent variables are essential for capturing non-local dependencies of the error on previous errors. Number two, the features that we leverage here will be residual based and cheaply computable because, as I mentioned above, not only does the error depend on the residual that we observe at each time step, residuals are actually at least elements of the residual vector are easy to compute via a ROM simulation. And this formulation that I'm presenting here is very general, and it encompasses a wide range of time series modeling methods, all the way from classical autoregressive models to more modern LSTM GRU models. So to give you an idea of how this might look in an LSTM setting, I've color-coded the different components of the classical LSTM architecture with the terms in this expression. And what you see is essentially, that even the most sophisticated kinds of time series models fit this general mathematical characterization. So how do we apply this in our three-step meta algorithm? So number one, we again do training, but rather than collecting snapshots of the high fidelity solution, what we do is we run our reduced order model at the parameter instances where we've already run a high fidelity model. We collect examples of the error between the high fidelity model and the reduced order model. Those are the responses, as well as the features. We grow these over time. We repeat this at different points in parameter space. And what this essentially yields are the requisite training data for regression, right? We have feature response pairs, and we have many of them. So at this point, we can turn the crank on sort of canonical supervised learning methods where, let me just get through this, where we essentially divide our data into training, validation, and tests. We train our model on the training data. We tune parameters on the validation set. And then we construct our noise model, that stochastic term, from the sample variance calculated on the test data. The next step is reduction. So once we've computed our machine learning error model, we introduce these into our reduced order model simulation. So given a set of inputs, our ROM executes. It generates outputs or quantities of interest. It also generates these features that are going to go into our machine learning error model as inputs. That will then spit out a machine learning error model, which has a deterministic and a stochastic component. And then at the end of the day, what we're going to do is we're going to add the ROM prediction of the quantity of interest to the stochastic error model to yield a distribution over ROM quantity or over high fidelity quantities of interest that captures the epistemic uncertainty introduced by the ROM itself. So we've executed this framework in a number of papers. Here's one example where we kind of run the gamut of a wide range of different features, which are different columns in this matrix, as well as regression methods from k-nearest neighbors all the way down to LSTM. I'll just point out a few important trends here. In the top left, I'm also plotting the result that you get from sort of the canonical Gaussian process method for quantifying errors. So what we see, first of all, is that RNN and LSTM methods yield the greatest accuracy on this problem. So even though deep learning methods have a lot of hype right now, empirically, they do outperform these classical time series models on our example. And we also observe that we get nearly 0.999 R squared values when we leverage only 7 elements of the residual. So what this means is that when we run our ROM simulation, we only need to compute 7 elements of the residual in order to get extremely accurate, near perfect representation of the ROM error. And so because this FEU value is so small, this implies that very, very little epistemic uncertainty is going to be introduced by leveraging a ROM here. So we get orders of magnitude speed up with almost no additional error or uncertainty introduced because we're now adopting this machine learning error models approach. So in this case, a traditional deterministic error bound would grow exponentially in time and would essentially overpredict the error by orders of magnitude in this case. So that's basically a summary of the 3 things that I wanted to talk about today. As one quick advertisement, I want to point out that the team at Sandia has been developing a very nice software framework to enable these types of reduced order models to be hooked up to many different kinds of simulation tools. At Sandia, there are obviously a broad range of simulation tools that operate across many different kinds of physical phenomena. And what we wanted to do was develop a general purpose open source tool that allows different kinds of simulation tools to expose the minimal required data and ingest the minimal required data. So basically the minimal API needed to unlock reduced order models for those applications. So if you're interested at all, you can go to github.com/Precio. And you'll see here's a little graphic of the minimal API that we require in your simulation code to enable these various different kinds of ROMs. And I'm showing on the left and right here a few applications that we applied the Precio framework to in the realm of hypersonic aerodynamics. And so with that, that's all the content I have today. I'd be happy to take any questions.
Thank you, Kevin. I don't know if I have to wait or I can begin asking questions. In any case, excellent talk, Kevin, honestly. Good. Here I am. So I have a few questions lined up. Let me begin in order. The first question is, how does all these AI-based model reduction deals with the strong singularities of the solution, say with shock waves?
Yep. So as you saw earlier, we're actually able to capture these discontinuities quite well through this, at least in the examples we've tried it on, which are 1- and 2-dimensional respectively. And that's because we don't rely on linear subspace approximations. I will say that, what we're relying on is sort of a well-posed initial value problem. So we do require for some of the analysis that there's a sort of a smooth dependence of the solution manifold on the parameterization itself, which will not always be the case for turbulent problem or for chaotic problems, for example. And so that's where we need to introduce methods like least square shadowing to smooth out the solution manifold such that a lot of the analysis works. But as I showed earlier, right, in some of those cases that are characterized purely by moving discontinuities, the ability to leverage nonlinear manifolds, in that case, they were generated by convolutional autoencoders, really allows you to capture these discontinuities quite well in a way that linear subspaces, no matter how you design them, simply cannot.
Okay. Next question is on the hyperreduction and associated with the quantities of interest. The problem that you show us at the end with the cavity problem, your quantity of interest was the pressure at one point. And therefore the hyperreduction, I know you are working on it, that's what you said. How is the hyperreduction affected when your quantity of interest, instead of being a point-wise value, is a sort of more global value? Say, for instance, a drag coefficient or a lift coefficient.
Right. So actually, the result here was the time average drag. So I'm showing the results here. So the time average drag was our actual quantity of interest.
Ooh.
And yeah, and the interesting thing when you go to nonlinear dynamical systems, unlike linear dynamical systems like balanced truncation, it's really hard to target the entire model reduction process to a specific quantity of interest because you can't decompose the state space naturally in a way that promotes observability of that quantity, for example. All the dynamics are kind of intermixed across the different states. And so our general approach here is to sort of leverage ideas of just like capturing the overall solution manifold accurately and viewing the solution with important physical properties that we know are important for the long time evolution of the solution. And then, at that point, we can target different quantities of interest. But as I'm sure everyone on the call knows, different quantities of interest impose different requirements on even the verification and validation studies that we have to do. So in our workflow, the place that we factor in quantities of interest is actually in the design of the original computational model, doing verification and validation with respect to those quantities of interest. And then at that point, when model reduction takes over, we basically apply sort of a general approach to get the overall model working well for the entire dynamical system. So none of this really is driven by a specific QOI. The QOI then does come back again when we talk about building error models for specific quantities of interest. So that last part of the talk, we do build individualized error models for specific QOIs. So again, it reintroduces itself there. But in terms of the hyperreduction itself, the projection scheme, we don't really factor in QOIs because it's a nonlinear dynamical system.
Okay. Another question. You actually motivated the talking about augmented reality, and we know that this is one of your final aims. restrictions. How fast we need the simulations to be? What's the resolution, both in time steps and spatial resolution, in order to be able to have something which is real augmented reality?
Right. So like current state of the art, generally people sort of think about 60 frames per second as being like the render rate. And so that's generally sort of the rate at which we need to extract simulation data from the simulator itself. So that's definitely a work in progress. I can't go into too much detail there, but I can say that we are investigating all of that right now. And in contrast to many of these applications, like sort of that real-time 60 FPS threshold is what we're trying to beat.
Okay, so we are still far away from these real-time simulations, I guess.
I would say we're getting pretty close. It depends on the set of physics that we want. So yeah, we should have more coming out over the next few years on that. If you're interested, we do have our first paper on model reduction put out from Meta over the last month, where we applied model reduction to the material point method, which is a popular method of computer graphics for simulating very complex reality systems. So we will have results coming out in the near term, I would say, on in terms of these real-time. Yeah.
Well, great. That with this answer, then I believe leaving everybody with these good hopes for the future that you will get some new results. I believe we can close this visionary talk, and we can thank you for this great presentation that you did. Thank you, Kevin.
Thank you so much.
All right, we are back. Thank you, Kevin. Thank you, Antonio. Kevin, it was really fantastic talk. Thank you so much. And guys, pay attention. There's a library out there where you can do, or at least try to do some of that stuff, okay?